Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever feel like your experiments are taking forever and you're not sure when to stop? Well, new research is making it way easier to get reliable answers faster. Today, we're diving into a fascinating new way scientists are thinking about gathering evidence in experiments. Imagine you're running a study, maybe a clinical trial or a psychology experiment. You collect data and you want to know if you have enough evidence to make a conclusion. The traditional way is to plan exactly how much data to collect beforehand and then analyze it all at once. This can be really inefficient, and sometimes you might stop too early and miss a real effect, or keep going way too long and waste precious resources. What if you could check your evidence as you go and decide to stop early if you have a strong enough answer, or even decide to collect more data if things look promising, all while keeping your statistical guarantees solid? That is exactly what this new framework, based on something called e-values, promises. Let's quickly talk about the old way. You are probably familiar with p-values. A p-value is like a fluke O-meter. The lower it is, say below 0.05, the less likely the result is just random chance. But there is a big catch. If you keep checking your p-value while collecting data, even if there is really no effect, you are almost guaranteed to eventually see a p-value below 0.05 just by chance. This is called sampling to a foregone conclusion, and it can lead to researchers believing in false effects. The researchers behind this work found that this problem with p-values gets worse the more you look at your data. They show simulations where, if you keep checking, you'll eventually reject the null hypothesis, which is the idea that there is no real effect even when it is true. This is a huge problem for science. So, what is the solution? E-values. Think of an e-value as a measure of evidence. It starts at 1, and if the null hypothesis is true, it tends to stay low. But if there is a real effect, the e-value can grow and grow and grow, potentially without bound. The key feature is that as long as the null hypothesis is true, the chance of your e-value ever crossing a certain high threshold, say 1 divided by your accepted error rate, like 20 for a 0.05 error rate, stays controlled. This is thanks to a mathematical principle called Wills' inequality. It essentially guarantees that even if you keep collecting data and checking your e-value, the probability of falsely concluding there is an effect stays low. This is a massive improvement over p-values, which become unreliable with repeated testing. And the coolest part, this works no matter when you decide to stop collecting data. You can stop at a pre-planned number, or if you see a significant e-value, or even if you run out of funding, or a reviewer tells you to keep going. All these different stopping scenarios are what the paper calls stopping times, and the e-value framework handles them gracefully. This also applies to confidence intervals. Normally, a confidence interval is only guaranteed to contain the true effect size at the single point you decided to look at. With any time-valid confidence intervals derived from e-values, the guarantee holds true at any point you decide to stop and look, no matter how you decide to stop. This means you can have confidence in your estimate even if you stop your experiment early. Now, translating this complex math into real-world use can be tricky. That is where tools like the SafeStats, our software package, come in. This package essentially does the heavy lifting, allowing researchers to design studies and perform these anytime valid tests and construct confidence intervals without needing to be statisticians themselves. The paper also looks at designing studies for maximum efficiency. They explain how to choose the best type of e-value process, called the fastest evidence accumulating e-variable, to potentially get to a strong conclusion with the fewest participants. This is crucial for saving resources, especially in fields like medicine, where participants' time and well-being are paramount. They even show how to plan your maximum sample size, called N-plan, based on how much power you want that's the probability of finding a real effect, if it exists, and the smallest effect size you care about. Interestingly, this planned sample size isn't a strict limit, it is more of a guideline. If your e-value crosses the threshold early, you can stop sooner, saving resources. If it doesn't, you know you haven't collected enough evidence to make a strong claim. This provides a built-in flexibility that classical methods lack. To show this in action, they looked at real psychological studies. In one example, they analyzed data from a study on moral typecasting. Using the e-value approach, they found they could reach significant conclusions with an average of about 73% fewer participants compared to the original study S approach. That is a huge resource saving. Another example looked at the Macbeth effect, the idea that feeling morally impure makes you want to cleanse yourself. Again, by using e-values, they could potentially detect the effect with significantly fewer participants. This shows that these new methods can make scientific research more efficient and less wasteful. So, what are the trade-offs? Well, sometimes to guarantee a certain level of power in the worst-case scenario, the planned sample size might be a bit larger than what you'd ideally need for a simple one-off classical test. Also, if you stop early based on data, your direct estimate of the effect size might be a little biased, though the confidence intervals remain valid. And like any statistical method, there is a choice to be made about which specific e-value process to use, which the authors recommend pre-registering to avoid any appearance of cherry picking. But these are minor compared to the benefits. E-values offer a continuous measure of evidence, meaning you don't just get a yes or no answer, but a nuanced understanding of the strength of your findings. They are also incredibly flexible, allowing you to adapt your data collection strategy on the fly without compromising your statistical guarantees. This is a major shift from the rigid protocols often required by traditional methods. Ultimately, this research is about making science more robust and efficient. It tackles the long-standing problem of how to conduct reliable inference when data collection and analysis might need to be flexible, which is practically the reality of many research projects. By allowing researchers to monitor evidence as it accumulates and adapt their plans, e-values offer a more practical and powerful approach to scientific discovery. It means we can get to reliable answers faster, with less wasted effort, and with greater confidence in our findings, no matter when we decide to stop collecting data. What do you think about this new approach to statistical inference? Does it make sense to have a flexible way to collect data and analyze results? Let us know your thoughts in the comments below, and if you found this breakdown helpful, please give us a thumbs up, subscribe to Rubin's Mind Lab for more science explained simply, and hit that notification bell so you don't miss our next video. Thanks for watching, and we'll see you next time.